Hello trigonometry students, welcome back. My name is Jamie Amy. Let's dive into our next set of material. An angle in standard position is an angle where the vertex is at the origin, the initial side is along the positive x-axis, and the terminal side is the other ray of the angle. That ray in position after rotation of the initial side is called the terminal side. Here in this visual, our terminal side terminated in quadrant 1. Here we have a positive angle in which the rotation of the terminal side is counterclockwise. I'm going to draw the x and y axis on this so that you can see why it is called a positive angle. Okay, so I've drawn the x and y axis strategically so that the vertex is at the origin and the initial side is here along the positive x-axis. But the terminal side, you might think at first like it opens this direction, but the red arrow, that will inform you of the direction of the angle. So this one did not just go straight to that acute angle, but rather it opened this direction to 90 plus that, passing 180, passing 270, and stopped right there on what we call the terminal side. Without this directional arrow, we wouldn't have known that though. So if you're trying to show that the angle is opened in this direction, make sure you add that arrow right there. Let's pretend that that is, let's say 310 degrees. Okay. Let's look at the same blue angle, but opening in the negative direction. Okay, so let me draw this again. The origin is here at C. The initial side is along the positive x-axis. And the terminal side, it appears to be in the same location as this one. But this one, a point on the terminal side, made a 310 degree rotation. And here, a point on the terminal side made only an acute angle, so somewhere between 0 and 90 degrees. It stopped right there. So let's pretend our same 310 was accurate. So if this direction was 310 degrees, then to find this one, you go, okay, well, it would have been 360 had it been a full rotation, but it's not a full rotation. It stopped short. It does not travel through 310 of the degrees. That would make it a 50 degree angle. So the measure of this angle right here would be 50 degrees, but it is a negative angle because it's this directional arrow tells us that it is. So this right here would have a direction of negative, measure of 50 degrees. Coterminal angles have the same terminal side and differ by a multiple of 360. For example, here we have a terminal side in quadrant 1. And should we have been given just this blue angle right here with this blue directional arrow, it would represent an acute 60 degree angle. However, this directional arrow makes a full 360 degree rotation and then an additional 60 degrees. Notice that it terminates at the exact same place. That is why we call them coterminal angles. I like to say that they terminate at the same location. So with this directional arrow, we know that we've got one full rotation, that would be 360 degrees. But for it to terminate at the same location, we would have to go an additional 60 degrees. So 360 plus that 60 degrees is how we get the measure of a coterminal angle, which is 420 degrees. Here's another example. Had we been given this obtuse angle, this blue one right here, and this directional arrow saying 110, we'd say, okay, that's it. That's a 110 degree angle. But this red directional arrow tells us more about a coterminal angle. One option, it says this terminal side made one full rotation, stop, so that's 360 so far, kept keeps rotating, an additional full rotation, stop for a second, that's another 360 degrees. And then it went an additional 90, 100, 110 and stopped right here. So it terminates at the same location, but the degrees that it traveled were 360 plus 360 plus 110, which is 830 degrees. All angles coterminal with theta are expressed like this. Theta, and then you're going to add a certain number of rotations, where n is any integer. An integer, recall, examples of integers would be -3, -2, -1, 0, 1, 2, 3. Those are all integers. So we could be adding 3 full rotations, or maybe even subtracting 3 full rotations. So remember that integers can be negative. And that will get us all coterminal angles to some theta. For example, express all angles coterminal with a 60-degree angle. Okay, so we're going to use this right here. We're going to write an expression. We want theta to be 60 degrees, so that will go first. Then we'll do plus n and 360 degrees, where n is any integer. It would look like this. 60 degrees plus n times 360 degrees, and then we state that that is where n is any integer. So this expression right here represents all coterminal angles to this 60-degree angle. We saw one example, 420, but there could have been, or there are many more. So if we add 360, we would have got to 420. If we went another full 360, what would that put us at? 780. We could have got another full 360. Well, that would put us at 11, do I need my calculator? 1140. We could have even gone in the negative direction. So take your 60 degrees, subtract out one rotation. It'll be coterminal. It would be negative 300 degrees. Subtract out another full rotation. That would be negative 660, I believe. Check my math with that. But to express all of these coterminal angles and more, that would look like this. 60 degrees plus n times 360, where n is any integer. Example, write the expression for all angles coterminal with an angle of 908 degrees. Then find the angle of least positive measure coterminal to that 908 degrees. Okay, first task, write an expression for all angles coterminal to 908. So we're going to write our 908 plus some number of full rotations, which we express as 360 degrees. So it would look like this. 908 degrees plus n many 360s. Second task, find the angle of least positive measure coterminal to 908 degrees. All right, 908, that's made at least one full rotation. I'm thinking 2 rotations and plus a little bit more even. So I'm going to pick my calculator up and I'm going to subtract out some full rotations. So I'm going to type in 908 minus 1 full rotation of 360. That brings me to 548 degrees. So 548 is a coterminal angle to a 908 degree angle. If you graphed both of them, they would terminate at the same spot, okay? However, the directions are asking for the least positive. So let's go again. Let's subtract out another set of 360. So type in 908 minus 2 full rotations. What you'll get is 188 degrees, and that's where you want to stop. If you subtract out another 360, you'll go into the negative range, which is fine. You'll find another coterminal angle, but they're asking us to find the least positive. So positive 188 degrees would be the least positive coterminal angle. Here's a nice visual for us. 908 degrees would rotate a full 360, another full 360, and then an additional 188. So what we did was subtract out. We subtracted a full rotation, subtracted the full rotation, and we found the measure between 0 and 360 called the least positive measure right there. It's coterminal because they both would look like this angle right here. All right, you try this one. Write the expression for all angles coterminal with an angle of negative 75 degrees. Then find the angle of least positive measure with coterminal to negative 75 degrees. Go ahead and pause the video and try that now. All right, welcome back. If you came up with negative 75 degrees plus n times 360 degrees, you got your expression correct. And if you added one full rotation to your negative 75 degrees, bringing you to 285 degrees, then you got that right as well. Here's a nice visual on that. Negative 75 degrees would terminate in quadrant 4. It would look like this. If you took that terminal side, that negative 75 degrees, and you added one full rotation to it, that would look like this. I'm going to put a point right here, okay? Follow this point. If you added 360 to it, that means adding, so we're going in the positive direction. So I would add a full 360 degrees to it and stop right there. That would terminate at the same spot, and that angle measure would be positive 285 degrees. Next, let point B be x comma y, and that is on the terminal side of an angle theta in standard position. We are asked to use the distance formula to find how far B is from the origin. All right, first thing I want you to do is draw this here. It's zoomed in on quadrant 1. I put B in quadrant 1 with coordinates x comma y. I know that the angle is in standard position, which is why I had to put one initial side on the positive x-axis and the terminal side here. Theta is at the origin, the vertex of the angles here. Knowing that B has coordinates x comma y, I know that the distance along the x-axis is x and the vertical distance is y. And now we're being asked to use the distance formula to find how far this origin point here is to that point x comma y. So we're being asked to find this distance right here. Okay, this is a right triangle, so you might remember Pythagorean's theorem that says the hypotenuse squared, okay, distance we're looking for squared, is equivalent to one of the legs of the right triangle squared plus the other leg of the right triangle squared. So we're going to use this, we're going to leave x and y variables, and we're going to solve for r. To solve for r, we need to get rid of this squared. How do we get rid of a squared? We square root both sides of the equal sign. And it turns out that the distance from point B to the origin is equal to the square root of x squared plus y squared. Now we're only going to be using the positive root, okay? R is always going to be positive for us. Let me explain why. X and y, that could have been over here somewhere where x is negative, y is positive. Maybe it was in quadrant 3 somewhere where x is negative and y is negative. Maybe it was in quadrant 4 somewhere where x is positive and y is negative. So x and y, the signs could change, but this distance, follow this point around this circle. This distance never changes. Why? Because it's the radius of the circle. Once the radius is set, the distance from the center of the circle to any point on the circle will be the same. That's why another reason why they use the lowercase r for x, y, and r when we're talking about an angle in standard position. So r for radius, which is always going to be positive. All right, let me erase that circle, so it's kind of a lot. And what I'm going to show you now is how we take SohCahToa. Now SohCahToa is for any right triangle where the two interior angles are acute. That triangle could be at any location in this rectangular coordinate system, at any orientation, okay? SohCahToa works. But what we want to do for trigonometry is take any triangle, any right triangle, in any location or orientation, we want to drag it over to this standard position. We want to drop it right there so that theta is at the origin, okay? We want to study triangles in standard position because what that does for us is takes away the restriction that it has to be a right triangle with two interior angles being acute. We could now take this theta and make it obtuse. Say its terminal side is here. From there, we could beeline it to the x-axis, creating this right triangle, and then we're going to use what would be called a reference triangle. Looks just like it, but it's in standard position. So here we would have the same. We'd have some x distance, it'd be negative, some y distance, some positive r distance, and we can study that in standard position. So it's no longer just right triangles with two interior acute angles, okay? So I'm going to show you how this is going to change. Ready? The side lengths of the right triangle here in standard position are x, y, and r. So what I want you guys to do is rewrite SohCahToa using x, y, and r instead of the a, o, and the h. All right, I'm going to erase all this other stuff and show you what I mean. Okay, currently y is what we would have called the opposite. So instead of O for opposite, we're going to change all the O's for opposite into Y's. The adjacent, we would have used A for adjacent. But we are not going to use A for adjacent. We're going to use X wherever we see A's for adjacent. And this, instead of the hypotenuse, we're going to use R. Okay, so here we go. Look at this. SohCahToa. Sine is going to be not opposite over hypotenuse, but y over r. Cosine, we're not going to call it adjacent over hypotenuse, we're going to call it x over r. Tangent, we're not going to call it opposite over adjacent, we're going to call it opposite, which is y, over adjacent, which is x. It looks like this. SohCahToa for an angle theta in standard position would look like this. Sine is y over r, cosine is x over r, and tangent is y over x. This is something that you're going to want to jot down, have it available for quick reference. It is a 9-letter way to remember the 3 trig functions, sine, cosine, and tangent, the value of their ratios in terms of x, y, and r. Okay, we study 6 trigonometric functions of angle theta. Sine, abbreviated SIN, cosine, abbreviated COS, tangent, abbreviated TAN, cotangent, abbreviated COT, secant, abbreviated SEC, and cosecant, abbreviated CSC. You can see on this figure here, which we've gone ahead and set it up on a unit circle. A unit circle means that its radius is 1, okay? So here, r is always equal to 1. Sine, you can see, is right here. And it's actually, that word comes from a chord. This sine theta right here is actually half of, should we had extended this chord to the other side of the circle. Let me show you where that's written down in the etymology of trigonomic function names. Sine comes through Latin from a Sanskrit word meaning chord. In the figure, segment AB has length sine theta and is half of a chord of the circle. So you can see that right there, half of a chord. Tangent and secant come from the lengths of a line segment that are either tangent or secant to a unit circle. So here you can see tangent. This line right here is touching the circle in exactly one location. Call that a tangent line. And the distance from that point on the terminal side to this point C is tangent of theta, which is the y coordinate over the x coordinate of this coordinate B. Secant is the distance from, well, here's our cosine theta. Secant's this distance here. Cofunctions are cosine, cotangent, and cosecant. So that's where the names came from. Sine, tangent, and secant, and then their cofunctions, cosine, cotangent, and cosecant. Some math classes will start with the study of sine, tangent, and secant, leading to the cofunctions. We start with the study of sine, cosine, and tangent, and then we talk about the reciprocal functions called cosecant, secant, and cotangent. Historically, there were more trigonomic functions, for example, verse sine, but those are now obsolete. However, new ones are also being studied. Here's an article that I found in The Onion. If you're interested, you should read it. It's about the study of 27 new trigonometric functions. Don't worry, we're not going to study 27 in our class, but it's a good article. It's interesting to see the way others are using trigonometry in their studies. We're going to be using sine, cosine, and tangent, and then their reciprocal functions, cotangent, secant, and cosecant. Last thing I want to point out is the connection between the last slide and this one. Sine of theta, we said in the last slide that that was equivalent to y over r. Well, here we said that this is the unit circle. So that would be y over r, the radius of the circle would be 1. So that would just be that sine of theta is equal to the y coordinate of b. So that's why here sine theta is this distance right there. It is the y coordinate of b. Cosine, we learned on the last slide that that is x over r. Well, in a unit circle, r is equal to 1. So cosine of theta in a unit circle is just the x coordinate of b on the terminal side. So you can see here, just the x coordinate is this distance right here. Cosine of theta equals the x coordinate of b. Sine of theta equals the y coordinate of b. Here's the x coordinate, here's the y coordinate. And then the last connection I want to make is that tangent we learned is y over x. That's not dependent on the radius of the circle. So this length right here would be, you take the y coordinate of your point B, divide it by your x coordinate, and you have the value of tangent. All right, let's look at those 6 trigonometric functions of theta in terms of x, y, and r. So our angle theta is at the origin, are in standard position. Sine of theta equals y over r. Cosine of theta equals x over r. And tangent of theta equals y over x, where x does not equal 0 because that would be an undefined value. All right, the next 3 I'm going to do will be the reciprocal functions. Sine's reciprocal is cosecant, so instead of y over r, it's r over y. Cosine's reciprocal function is secant, so instead of x over r, it's r over x. And tangent of theta's reciprocal function is cotangent theta, so instead of y over x, it's x over y. R for all 6 will be the square root of the x-coordinate squared plus the y-coordinate squared. xy is any point on the terminal side of theta, which needs to be in standard position. Just to overemphasize the reciprocal functions for you, I wrote them down here. Sine and cosecant, reciprocal functions. Cosine and secant, reciprocal functions. Tangent and cotangent are reciprocal functions. Okay. Example. The terminal side of angle theta in standard position passes through the point 8, 15. We're being asked to find the values of the 6 trigonometric functions of an angle theta. All right, so we're going to start by using the point 8, 15. That gave us our x as 8, our y as 15 from right here. And, well, to find the values of the 6 trig functions, we need x, y, and r. So the only one we're missing is r. But we can find r. We know that it's equivalent to the square root of x squared plus y squared. So we plug in 8 for x, 15 for y. Do our squaring first, then the addition, then square root 289, and we find that r equals 17. So we actually ended up with a Pythagorean triple. Here's a figure for you to refer to. 8 is the x-coordinate, 15 is the y-coordinate, and r, this is not the unit circle this time, okay? The radius of this circle, or the hypotenuse of this triangle, is 17. Since all 3 side lengths of the triangle are whole numbers, it's called a Pythagorean triple. Okay, let's plug them in. Sine of theta is equivalent to the y-coordinate, 15, over r, which is 17. Cosine of theta is equivalent to the x-coordinate, which is 8, over r, which is 17. Tangent of theta is equivalent to the y-coordinate over the x-coordinate, so 15 over 8. Okay, the next 3 that I'm going to do will be the reciprocal functions. So sine's reciprocal function is cosecant. So instead of 15 over 17, it's 17 over 15. Cosine's reciprocal function is secant. So instead of 8 over 17, it's 17 over 8. And tangent's reciprocal function is cotangent. So instead of 15 over 8, it's 8 over 15. I want to point out that these are the exact values of the trig functions. Had you been asked to approximate these to the nearest tenth, you could just pick your calculator up and type in 15 divided by 17. Let me actually do that right now. 15 divided by 17, rounded to the nearest tenth, is approximately 0.9. Let's say you were asked for this one in approximation to the nearest tenth. I can do that 17 divided by 15 in my calculator. I get 1.1. So depending on how the question is worded, if they're asking you for the exact value, you're going to want to put these values that I'm boxing right here, these ratios. But if they ask you to approximate, then you can type that into your calculator and do so accurate to as many decimal places as are requested from you. One more thing I want to point out before going to the next slide is when you're in My Lab and Mastering, the program will often ask you for your answers in this order: sine, cosine, tangent, followed by cosecant, secant, cotangent. However, it will also ask you in different questions for your answers in this order: sine, cosine, tangent, followed by cotangent, cosecant, and then, secant, and then cosecant. So just be careful. I don't want you to do all this work and then accidentally type them in the wrong order. So My Lab and Mastering is very good about asking you for a value. It'll have a blank where you enter your answer, and then directly below the answer in parentheses and written in dark blue, it'll tell you exactly how they want the answer. So it'll say like approximate to the nearest tenth. So you would type in the 0.9. Or it won't say approximate, which means you have to give the exact, So that would be the 15 over 17. It would say something like the most simplified fraction. So 15 over 17. The program My Lab and Mastering is very good about this. So if you're ever wondering, how should I be entering the answer here? Look directly below the cell in parentheses, often in dark blue, and it will tell you exactly how it wants the answer. All right, I hope that helps. We're going to do one more slide before we go to the homework. Example, find the 6 trigonometric function values of theta in standard position if the terminal side of theta is defined by x plus 2y equals 0 and x is greater than or equal to 0. Okay, we know that to find the function values, we need x, we need y, and we need r. But we don't have any of them. We just have the equation of the terminal side. Okay, no problem. We're going to do some algebra skills and try and figure out what point will make this equal to 0. And we also need to remember we need x to be positive. So maybe you can just eyeball it. Like if x were equal to, let's say 1, because it needs to be positive, then y would need to be something about a half. Well, you can solve for y if you want. So let me write the whole thing equals 0, and let me solve for y. I'll subtract 1 from both sides, and then I'll divide both sides by 2. So y would equal 1/2. So you could go with that if you want. X is equal to 1, y is equal to 1/2. So our point would be 1, 1/2 on the terminal side. That would work. Then you could find your r by doing the square root of x squared plus y squared. And that would give you a radius of square root of 1 plus, this would be 1/4. 1 plus 1/4 would be 5/4. So that would be the square root of 5 over 2. Square root of 5 over 2. Okay, so you could go with these values if you want. You can use x equals 1, y equals half, and r equals radical 5 over 2. I'm thinking I don't want to work with this 1/2 and this fraction here, so I'm going to go for a different point. I'm going to try, let me erase all this work. I'm going to increase the x to a 2, because just thinking ahead, I'm thinking that's going to give me a whole number for y. So if I change my x to 2, and now I solve this for y. I subtract 2 from both sides. Oh, no, that should be -2. My mistake. Sorry. Subtracting 2 from both sides gives me 2y equals -2. Divide both sides by 2. And I get y equals -2 divided by +2, which is -1. I like this better. I'm going to go with x equals 2, y equals -1, and that would make my r equal to the square root of 2 squared plus -1 squared. Doing the squaring first would give me 4 plus 1, which is 5. The square root of 5 is not a whole number, so I would work with it in its exact form, square root of 5. So that's what I'm going to use, 2, -1, and 5. You can use the other option or find a different option if you want. As long as you find a point on the terminal side, all of our answers will end up being the same. Okay, here we go. Let's write that solution up. Any point that satisfies x plus 2y equals 0, make sure you follow your restriction, x needs to be positive, is on the terminal side of theta. One option that I'm going with is 2, -1, giving me an r of radical 5. Here's a visual. Turns out that terminal side is in quadrant 4. And to graph it, if you'd like, you just plot your point to -1, 1, 2 on the x-axis, -1 on the y, and then you draw your terminal side passing through that. We also figured out that the distance from the origin to that point is radical 5. If you're using our point from earlier, I'll show you how that is also on the terminal side. Our point from earlier was +1 on the x-axis and then -1/2 on the y-axis. So hopefully you can see that that point is also on the terminal side. And actually, we found that the distance between the origin to that point was radical 5 over 2. I don't know if you remember that. So it's half of that distance there. So hopefully you can see there that either of the points will work. In fact, any point on this terminal side will work. Once we reduce our answers, we'll all get the same thing. All right, here we go. Let me erase all this. All right, let's go with sine first. Sine is equivalent to, you might want to jot this down, S, Y, R, C, X, R, T, Y, X, okay? So sine of theta is equivalent to our y coordinate over our radius. So it looks like this here. Sine of theta equals y over r, which is -1 over radical 5. This, you guys, this is the trigonometry portion of the question. We've done the trigonometry. Everything that follows is just algebra. It's called rationalizing the denominator. Multiply top and bottom by radical 5, and we get an exact value, which is considered the most simplified as negative radical 5 over 5. This is exact. Had they asked you to approximate it, you could have typed in the -1 over radical 5 from here and given them as many decimals of accuracy that were requested. All right, let's do cosine next. It is x over r. Cosine of theta equals x over r. X is 2 over r, which is radical 5. This is the trigonometry portion of the question, okay? Everything that follows, you guys, is just algebra. We're rationalizing the denominator by multiplying top and bottom by radical 5, which gives us an exact value of 2 radical 5 over 5. These are what you're going to want to type in to MyLab and Mastering as the exact values. If they ask you to approximate, you can give a decimal, but if they don't say approximate, then don't do it. You've got to give these exact values, which are in simplified form once you rationalize the denominator. All right, let's go again. Tangent is equivalent to y over x. Looks like this. Y is -1, x is +2. So -1 over 2. This is the trigonometry portion, and there is nothing to simplify, so -1/2 is our most simplified value for tangent of theta. All right, so we've got the first three, sine, cosine, tangent. Let's do the next three. I'm going to go with cosecant next. Cosecant is the reciprocal of sine. So instead of -1 over radical 5, I do the reciprocal, which is negative radical 5. Or you can take it from here, r over y. R is radical 5, y is -1, and that simplifies to negative radical 5. This is the exact value of cosecant of theta. Okay, I'm going to do the reciprocal function of cosine next. That is secant of theta equals, and instead of the 2 over radical 5, I put radical 5 over 2. You could have also taken it from here. Instead of x over r, it's r over x. R is radical 5. X is 2. And there's nothing to simplify or rationalize there. Last one, I go with the reciprocal of tangent, which is cotangent of theta. So instead of -1/2, the reciprocal of that is -2. Or you could take it from here. It's x over y. X is 2, y is -1, and that simplifies to -2. All right, these are the exact values that you would type into the program, okay? All right, you guys, we are going to stop the video now. I want you to go to My Lab and Mastering. You're going to do Chapter 1, homework questions number 15 through 27, okay? You should have done 1 through 14 after the first video. Pause it, do those. Now here, stop the video and do 15 through 27. All right, thank you for being here. My name is Jamie Amy, and I will see you next time.